This video is going to cover continuity in the limit process. So this should be your sixth entry in your table of contents. The target for today is students will apply the definition of continuity using the limit process to determine if a function is continuous at a given value. So we're going to kind of do this lesson in two parts. Part on this video, of course, and the next part in class the next day. Because let's kind of talk about what it means to be continuous. There are three examples of discontinuities of a function over an interval AB. The first thing I want you to notice is that when we talk about this interval AB, let me get a pen, this interval AB, you'll notice that it's an open interval, meaning that our endpoints are not included. Okay, so when we talk about continuity, we're going to start talking about continuity at a specific point, not over the entire function, because our functions are going to be continuous, but they're not going to be continuous everywhere. Some functions are, some are not. Okay, so three big things that we look for with continuity are on these pictures below. The first one being that our function is undefined. So one of the types of discontinuities is because our function is undefined. So if we look at our C value, that value right there, and we go up, that means that open point means our function is undefined. Okay, so that is a discontinuity. Okay, and we can see that easily from the graph. The second part of types of discontinuities happens when our limit fails to exist. And we've talked about this graphically. So for instance, at that C value, we can see there's a jump discontinuity there. We know our limit fails to exist there. On the one below it, we have a vertical asymptote there at that C value. Again, limit does not exist. Goes to infinity, positive infinity, or in negative infinity and positive infinity, or both. And then the last one, types of discontinuity, happens when our limit exists, our function exists, but they're not equal. That's kind of the most confusing one. So just really quickly, if we look at the limit as we approach C, from the left and the right, we clearly see that the limit is going to exist at this L value. But our function is defined there. Our limit and our function are not coming into agreement with each other, and that's kind of one of those discontinuities, and we talked about that when we talk about limits by graph. Okay, so when we talk about continuity and the definition of continuity, three things have to happen in order for us to say it's continuous at a specific value, at this x equals c. Remember, c is just a generic x value. The first thing that has to happen is that our function at the value f of c, remember c is just any value for x, has to exist. Okay. Function has to be defined. So if we look at our graphs, our first one, our function was not defined. Second one, that one right there, sorry, I'm moving the picture, not the actual thing. So our second one here, our function is defined there, but that limit doesn't exist, okay? So that one would be okay. And then the last one, our function is defined. So good. First part of continuity. Second part of continuity is that our limit, as we approach the specific C value for this function, also must exist. Okay, so the limit must exist. First picture, limit exists. Second pictures, our limits do not exist. Third, our limit does exist. And then the third and most important thing is that our limit, as x approaches that C value for the function, must equal the function at that value. And that is probably the most important part of the definition of continuity. Okay, that our limit and our function must come into agreement. And if we look at all three of our pictures above, sorry, let me kind of put them back where they should go. If we look at all three of them, not one of them is that third condition happening. Okay, so we use this definition, these three parts of the definition of continuity, or the three criteria of continuity, to kind of prove whether a function is continuous or not. So I'm going to throw an AP problem at you guys. Not like that. Let's go and arrow down to that point. Okay, so this is actually a free response question from the 2011 AB exam, and it is our number 6. No calculator was allowed on this one, so you had to be able to prove continuity using those 3 criteria. And what we want to do is to prove that each one of those things is happening. So it says let f be a function defined by f of x. It gives us a piecewise function. And then it says on A, show that f is continuous at equals 0. And we're choosing 0 specifically because that's where that jump occurs, or possible jump. So we're going to prove whether the jump is there or whether it's not. Okay, and we kind of talked about how to prove limits when it comes to piecewise functions. So we're going to use all that stuff as well. So the first thing I'm going to do is go back to that definition and that criteria, that 1. I want to prove that the function exists at 0. So I want to see what f of 0 is. So now I'm looking for the equalness, which is that top one. Okay, so I'm going to plug it into that top one. So 1 minus 2 sine of 0. Now the sine of 0 is 0. 2 times 0 is 0. So we wind up getting that this is equal to 1. Okay, so my function does exist. I got a value back. It's good. So part 1 for my criteria is good. Second thing I want to do is look at the limits. Because of the fact that this is piecewise, remember we're going to have to do a limit from the left and a limit from the right to prove that the limit does exist there. So I'm going to just start doing that. Limit as x approaches 0 from the positive side. The limit as x approaches 0 from the negative side. The positive side being the greater side, so e to the negative 4x. We definitely want to show this. And the bottom, 1 minus 2 sine x. Okay, so now we're just evaluating the limit algebraically. We're plugging in a 0 in for the x. So on the top one, if we plug in a 0, we get negative 4 times 0, which is 0. E to the 0 power is 1, because anything to the first power is 1. Anything to the 0 power is 1. And then, of course, we kind of already plugged it in. We know that's 1. So we now can say that the limit as x approaches 0 of this function is in fact equal to 1. Okay, so the second criteria is true. The limit does exist. And then, of course, the third and most important part. Does the limit as x approaches c of this function equal f of 0? And I'm sorry, our c value is 0 here. Okay. Well, we know that the limit is 1, we know the function is 1, and those, in fact, are equal to each other. So I'm going to put a little check mark there. Because all 3 of their criteria were met and are true, therefore we can say, remember that symbol, therefore, f of x is continuous at x equals 0, answering the question. Okay, so that's kind of what it means to prove continuity of a function. Now, when it comes to continuity, there are 2 types of discontinuities. Okay, I'm going to go on to the other page. So there are 2 types of discontinuities. They fall into one of these 2 categories. One being that they are removable discontinuities. Okay, and the second one being that they are non-removable. So either we can remove them or we cannot. Okay, so we're going to stop the video there. This one was short. Like I said, we're going to do this in 2 parts. When you come in tomorrow, you'll do the warm-up that is below, and we will start the second part. So if you have any questions, let me know.